broader objectives of Q. Specifically, in this case, we're going to be diving into Hypersync in the context of what is the difference between a hypergraph and a blockchain? How does Hypersync quickly perform synchronization of massive amounts of data between different parties? That's kind of the question we'll tackle next. And then after that, if we have enough time, hopefully we will, then we'll dive into the topic of our meta virtualization feature, which is going to be coming up later this year. And so to get started on Hypersync, we'll talk about the notion, of course. Previously, I've talked about what a hypergraph is, but short story if you haven't been around for that before. If you know what a graph is, it's pretty simple. It's either directed or undirected. It's vertices connected to each other by a series of edges. Some graphs allow you to have multiple edges connecting to the same vertices, so you'll have like two different edges. Sometimes they don't allow that. They only allow one edge. Sometimes they're directed, so there's an arrow that points one of two ways. Sometimes there's rules about the graphs where you can't have cycles in the graphs if it is a directed graph. All of these things are really cool and have led to a lot of unique technologies that have been built. Graph algorithms are used for things like input lookups, like when you are typing into a message on Google or typing into the search box on Google and it's giving you autocomplete suggestions. That's actually a graph search algorithm that's producing those set of results for you. And so graphs are really useful. But graphs don't capture all the elements of the world, all the things that we need to do to reason about or associate data with one another. There's simply not enough dimensionality. And so what hypergraphs are is essentially adding that extra degree of dimensionality. It's breaking one of the rules. Instead of an edge just being two vertexes connected to one another, it is an edge that can connect multiple vertices together. And so depending on the nature of how you draw a hypergraph or represent it, there's like two pretty common ways. You just draw like a blob around the vertices, or you'll draw this like weird funky line that looks kind of like this, that like intertwines the two connections there into one singular connection between the three. Whatever the case, a hyperedge is basically an edge that connects more vertices together. And just like regular graphs, they can have the same rules where there's arrows, that you can have the same ideas that there's like no cycles between these. And then there's also another degree of dimensionality that exists where hyperedges can also encapsulate in some systems hyperedges themselves. So an infinite recursion of hyperedges can unlock a lot of interesting data models. But what's really important for us in Quilibrium and why we are building around this hypergraph model is the fact that hypergraphs actually can encapsulate practically every data structure that we would possibly be interested in. Hypergraphs, like if you've been in computer science in college, you've probably heard the argument that like a hash map is basically the same thing as a graph because you can represent this key value association that can point to other elements, and that essentially is the same thing mathematically as the construction of a graph. But when you get into what hyperedges can represent in terms of relationships, it unlocks a lot more than just like a simple set mechanic, a simple key value set. You can do all sorts of associations in the point where you can actually extend out the entire relational data model. So when you're talking about RDBMSs like MySQL or Postgres, if you're talking about wide column databases like Apache Cassandra or key spaces on Amazon or SiloDB, these are all things that can be represented in the hypergraph model. And when you talk about the nature of how you structure data and you enforce the validations of that data, the schema that represents that data, the schema itself can be represented on a hypergraph. And so that's the reason why we use a hypergraph, because hypergraphs can encode those relational bindings and enforce them structurally without having to actually implement those specific rules unique to each specific situation. If you instead encode it to the hypergraph will naturally enforce it through the use of its rules. So that's really cool. What does that actually mean? When you are building a application that is using blockchain, for example, a blockchain is, simply put, a collection of blocks that contains a root element in its header that points to a series of state transitions. And these state transitions are encoded as a collection of usually transactions, and they are collectively, hierarchically placed into a tree structure called a Merkel tree. And the purpose of a Merkel tree is to essentially encapsulate, and this depends on how you do it, like if you do like zero leaves, or if you just simply traverse all up all the way. Either way, if you are constructing a Merkel tree from these events, you then essentially are taking the hash of these leaves together into the next rolling item up the tree, the next branch. So in other words, hash of transaction 1, hash of transaction 2, and then hash of those 2 hashes. And then the same thing at the next level, all the way up to the root. And then that root is encoded and stored in the header of the block. And then, of course, all the transactions are included in that same block. And then the network publishes that block of transactions. The reason you would do this is because you want something that sequences data in a linear fashion. You want every single event to have a strict global ordering. And that can be very useful for things that conflict with one another. Where that gets problematic is when you're trying to encode a lot of data in a lot of events. And so you'll see a lot of these networks come up with really interesting ways, like these various crypto networks that exist. They'll come up with interesting ways to try to address the speed bottleneck that happens with this. And so sometimes you'll have approaches that use sharding in order to have each individual shard of the network, whether it's a collection of addresses that have balances or a collection of unique properties that essentially dictate that this transaction would fall under this shard. Whatever strategy they're employing, they'll just have an individual quorum for each individual shard, and then collectively they will be responsible for maintaining their shard state, and then there is a larger consensus wrapped around the collection of shards. This is kind of essentially what Near protocol does with their Nightshade consensus. It's also what we use for Snapchain at Farcaster. And that works when you are limited to a small series of state changes that are going to be recognized across all of the shards. And it will work very well for high throughput situations when you know that you have a minimal amount of conflicts. And those conflicts will almost always be strictly bounded to whatever your shard logic is. In our case of Snapchain, it is based on accounts. In the case of Near protocol, I believe it's also based on accounts. But at the end of the day, the purpose of these shards is a way to essentially delegate how much of the work is being handled by each individual node that is being used for consensus. And in the typical blockchain fashion, you still end up with a header that has a block hash, and then you have a reference to the previous, I screwed that one up here. You have a reference to the previous block hash in that header. So I put this in the wrong place. Let me go ahead and change that here. Great. And then usually there's like some other hash that is basically an unforgeable value for the entirety of that block. In the case of Bitcoin, that hash is actually used to determine which is the winning block, the proof of work algorithm. But at the end of the day, like there's just some sort of basis that uniquely characterizes that block. Cool. Okay. So that's essentially the structure of a blockchain. That level of performance means that you are limited in the nature of what kind of applications you can build, as I said. Even if you do something like sharding, you still end up with a scenario where you have to limit the amount of throughput because there is an intrinsic bottleneck. No matter how far you shard the network out, there's still an intrinsic bottleneck because you still have to have block producers, and those block producers are still going to have some amount of data that they have to hold and collectively maintain consensus over for the network to not halt. So that is the problem with blockchain. And what we're doing differently with the hypergraph model is that the hypergraph model is not even something that operates as a doesn't operate as a Merkel tree, like the underlying structure of the hypergraph and how it's maintained is in a Merkel tree. We actually use a different structure. It's called a Merkel tree. It's pretty similar in the sense of how, the purpose of it is a vector commitment scheme, but the difference is that we use the Merkel tree because it makes our proofs a lot smaller. And proofs actually matter for us because unlike sharded models like the one over here, that particular model requires data to still be passed around. So if I was account 1 over there and I wanted to prove to account 2 that I exist and I made these posts, I would actually have to send a whole lot of data over in order to converge on an accurate Merkel tree proof. Whereas a Merkel tree has this really cool property. So let's say that I have a singular point of data, and I've got 1 billion records that fall under this particular Merkel tree. If I wanted to prove that to you, depending on the actual branch width of the tree, And in the case of Quilibrium, our our app trees are at 64 branch width. So essentially log 1 billion records divided by log 64, that's about 4.5. So when you consider the fact that the root is shared across the network as part of our actual global consensus, we just care about that root point. That actually ends up with, in order for me to prove any piece of data on the network to you, I only have to send you 4 points. And so it would be those 4 hops on the tree that essentially encodes that piece of information. But this is a hypergraph. It's not a tree. So why is this tree here when we're talking about a hypergraph? And so this comes back around to the other scalability concern. If I wanted to prove data to you, or I needed to relay this data to you, you have to go through a lot. You have to go through the process of obviously receiving whatever that transaction was, receiving the proof that that transaction was appropriately encoded into the global state, and then I also have to evaluate that its presence in the tree was accurate, that the sequence of events wasn't played out of order, all of these different elements that relate to you having to handle a lot of encoded state transitions versus something that is just implicitly true. And so the nature of how we do things in the hypergraph for Quilibrium is that when you are making a change, that state transition has a proof associated with it. And that associated proof is essentially determining the validity of that state change in the first place. And because the amount of proofs that you have to communicate over is strictly bound to those specific linear steps in the hierarchy of the tree, you actually have enough data that you can very quickly send 2 pieces of information over, which would be the proof and then the lineage proof of the tree membership. And then from the tree, in order to actually represent this hypergraph data, we essentially, I believe I mentioned this in the previous stream, but I will go ahead and write it again. We essentially do a two-phase set, and that is encoded as a tree. So two-phase set is essentially adds and deletes. So if you've never done CRDTs before, or conflict resolving data types, I can never remember what that is, you essentially end up with these 2 grow-only phases of sets that encode that data. And so one is our vertices, one is our hyperedges. And then from that, you end up with essentially 4 collections of trees. One is the additions tree, one is the deletions tree for vertices, and then the second set of those 2 trees is for hyperedges. And what you can do from that data is, because I have given you a proof of that state change, and I've given you the lineage proof of those vertexes, you also have enough information to check on the corresponding other tree to confirm that that data hasn't been deleted. And so by consequence, you have something that, based on the fact that you're only needing to keep track of the roots that are collectively being shared across the entire network, I only have to give you a very tiny amount of information for you to validate that the data is correct and that that data has not been removed due to a state change. So that actually saves, you as a user of the network a lot of time and a lot of effort, or as a node on the network, a lot of processing in order to feel assured that the data and the action that is being passed to you is accurate and something that you can actively act on right now. Finally, the other aspect of this is that because this is a tree structure for these pieces of data, and because the individual commitment schemes have an intrinsic polynomial nature into the representation of this data, you can choose what sections of the tree it is that your node is going to be able to cover. So by consequence, you can actually make your node process only a specific subset of the shards of data, such that you can cover what is capable of your node to be able to handle. So in other words, you can limit it. I'm only going to cover half the network. Okay, then I've only covered half the network, and it's easy to divide that. Things like that. I am unfortunately running very low on battery, and I've also hit the time limit, so I'm going to wrap this up real quick. So this difference of why we have this is important for being able to represent incredibly large amounts of data, perform incredibly large amounts of operations on that data very quickly, and most importantly, be able to synchronize those changes on that data very quickly, which is the reason why when I did the replay earlier, I was able to evaluate over 1 billion state changes in approximately 23 minutes, which is somewhere around 750 operations per second. And that's just for a single shard. When you expand this out to the overall number of shards that exist on the network, that actually becomes really, really impressive in terms of how fast you can scale out the network and how widely you can scale out the network. And so that's kind of the reason why we're doing hypergraphs versus blockchain as our data structure of consensus. And then additionally, Hypersync is essentially just a tree walk algorithm where both parties are walking down the tree simultaneously, picking out the things that don't match. Because again, this is a polynomial commitment scheme, you will know at a given branch whether or not there is any further to go, because it will either have the same proof or it won't, and that'll tell you to keep going. And that works relatively quickly now that we have worked out all the bugs, if you have been following the testnet channel. So I hope that helps in explaining the difference between those two things. I'm sorry to get so abrupt on the wrap-up, but unfortunately I do not have my charger cable on me at the moment, and I am going to have to end the stream before the stream ends itself. So let me take a moment to ask folks if you have any questions. This would be the time to do it while I still have 8% battery life left, and then we'll wrap it up from there. Okay. Oh, okay, so I see a few questions. There are a lot of questions on Twitter, primarily by Easy Trades. Unfortunately, I cannot answer some of those questions because those are price related and speculation related. And as we said at the beginning, we do not encourage or condone speculative mindsets around the utility token of the network, so we won't comment on that, simply put. In terms of, yeah, let's see if there's, okay. How many people are developing 2.1? We have, so at the company, we now have 3 individuals that are working at the company, excluding myself, obviously. I remain the unpaid intern of Q. Outside of Q, there have been 37 contributors to the protocol itself, some at varying degrees of capacity than others. So some have contributed a lot more, some have contributed only a little bit, and that's just in terms of actual code. There's also been a few contributors who have contributed reports that either were performance related or even vulnerability reports historically, and additionally reported here's where it happened, here's why it happened. So it's more than just like a hey, this is happening report, but rather here's how this is actually happening and here's what you can do to fix it. So there are people even outside the 37 developers that are directly on the Git log as being contributors to the protocol. Link to the testnet channel. So we have 2 testnet channels. There's one on the community Discord and there's one on the Node Runners Telegram. We were originally trying to limit the Telegram because we were wanting to get people onto Quorum. Unfortunately, ironically, this Hypersync algorithm is something that we need to get onto Quorum so that we can resolve one of the most painful bugs Quorum is currently experiencing. Once we do that, then we'll move everything over to Quorum, but that has gotten in the way of that. Okay. I think that's it. I don't see any more questions, so I will go ahead and wrap it up here. All right, everybody. Thanks for attending, and I guess we'll